Hi everyone, we're Group 1, and our project is the Greenhouse Environmental Analyzer of blue-red light, humidity, temperature, and CO2. This is our group consisting of 2 PSCs, 1 EE, and 1 CPE.
Hi everybody, my name is Maya and I'm going to talk a little bit about the motivation and background of our project. So if you look on the right of the screen, there are some statistics from the National Agriculture Statistics Service from a 2022 census. So as of 2022, there were 30,000 farms in the US using greenhouses, and within those greenhouses, 839 million square feet were used for floriculture and 133 million square feet was used for food crops. This is an 118% increase in square feet of food crops from 2017 to 2022. So the motivation for our project really stems from this increased use of greenhouses in the US. And in the very sensitive and necessarily stable environment of these greenhouses, there is an increased need for reliable and easy to use greenhouse monitoring systems. Our device aims to measure 4 parameters that are typically controlled within a greenhouse. This includes temperature, humidity, carbon dioxide, and light levels, specifically red and blue wavelengths of light. Usually, multiple devices are needed to measure all of these metrics. However, we aim to create one all-inclusive device that is easier to use than all of the others. Temperature, humidity, and CO2 are very commonly monitored parameters in greenhouses. However, why are we looking at red and blue light levels specifically? Well, this is because blue and red light have been shown through research to positively impact morphogenesis, metabolism, and the capacity for plants to photosynthesize. More specifically, the blue light affects the chlorophyll production, which in turn affects the strength of the stems and the leaves, while red light has an effect on the flowering and fruit production of the plant. This is why we included monitoring the ratio of red to blue light in the greenhouse as part of the optics part of our project. Here's a quick visual for how we aim for our project to function. The device will be put inside a greenhouse, preferably at plant canopy level, and will continuously monitor the parameters. Along with this, there will be an application that can allow for remote viewing of the metrics from your phone, and as a stretch goal, we will be able to control the parameters of the greenhouse to keep the readings at a desired level. This will be talked about more in the later slides. Getting into our goals and objectives, some of our basic goals are that our device will be capable of detecting temperature, humidity, and CO2, as well as detecting white light and the red to blue light ratio. The measurements of these parameters will be determined and wirelessly sent to be displayed through our application. Our device will also be able to continuously collect data and update the application in real time, as well as satisfy the voltage requirements aligning with the senior design standards. Our basic objectives include successfully calibrating the bot sensors to ensure reliability and accuracy, successfully calibrating our light sensors with lenses and other optical elements to ensure overall white intensity and red to blue light ratio is accurate, as well as creating a software structure where the readings from the sensor will be displayed, and ensuring the measurements are read in specified intervals of time so the app can be updated in real time. Also implementing a power distribution network. For the sake of time, we will quickly go through our advanced and stretch goals and objectives. Essentially, for our advanced goals, we want all of our measurements, CO2, temperature, red to blue light ratio, etc., to be accurate within a set standard, as well as the total dimensions of our device to not exceed 15 by 15 by 10 inches. Our advanced objectives include calibrating all of our sensors and our photodiode to ensure accuracy, creating a housing in a CAD software where we can specify the measurements to not exceed our specifications, and communicating with all the sensors through only one I2C bus using an I2C splitter. For our stretch goals, we hope that the data collected through our device will eventually be able to be used to predict greenhouse status, determine parameters that must change for optimal plant health, and eventually be able to control the greenhouse parameters to adjust them accordingly. In order to achieve our stretch goals, our objectives are to create an option within the app to input the specific type of plant that's in the greenhouse and use data analysis of the readings to predict the plant health, establish a firmware and hardware that allows the dispositive to understand the data and analyze it to determine the changes needed within the greenhouse, and lastly, send signals from the device to the greenhouse itself to adjust the parameters however it determines necessary.
So here's our table of engineering specifications. You can see a whole list of different specifications from temperature to CO2 to humidity. The one that we will highlight is the lux value, and our requirement is for our sensor to be able to measure between 10,000 and 100,000 lux within a plus or minus 10% range of the actual value. There are some more specifications having to do with frequency, with power, and with some physical characteristics of the system. You'll see three more requirements listed on this page. One of them has to do with how heavy the actual device is, but the other two are highlighted. And so our first highlighted requirement is for the time between the updates of the measurements in our app to be realistic. We put that as being less than 40 seconds. And the second highlighted requirement is for our device to use the specified voltage, which is 9 volts. This is the start of our technology comparison and selection. So on this page, we will be comparing light sensor technologies. So we have the photodiode, the phototransistor, and the photoresistor. We chose the photodiode because of its very cheap cost, its very fast response time, the fact that it has a linear relationship with its values, and the fact that the current is what is being measured, which is what has the linear relationship with the values. So we had three different light sensor options, but we chose the VEML6030 because of the price range, the fact that it can measure up to 120,000 lux, which is above the 100,000 that we need, and its responsivity curve is pretty uniform. So there are four different types of lenses that we can go with. For this design, we went with the fisheye lens. Our previous design went with the plano convex lens, but because we need an 180-degree field of view, we went with the fisheye. And so here are the fisheye lenses we compared. As you can see, very different price ranges. And so we just went with the cheapest one. We thought we'd try it out, and so we did. And it seems to be reliable so far. So I'm very happy with it, and very glad we didn't have to spend $835 to do that. Here are two different filter types, dichroic and absorption. Our original design was dichroic, but since we're not using that design anymore, we're going with absorption. Absorption filters are much cheaper. They're not angle dependent, which is great for our design. They have the possibility to fluoresce, but we're not super concerned about that based on the filters that we have. And also, based on the filters that we have, we are not super concerned about the not as strong wavelength cutoff. These are our different filter choices. As you can see, Edmund, Kodak, and Lee. We went with Lee gels because it seemed that the cutoff quality between the red and the blue were the best with it. I was able to find filters that cut off pretty much exactly where I wanted them to in the spectrum. So you can see the blue is very contained within the blue, and the red is pretty relatively contained within the red. And that was better than any other filter we could get for the price range. And so that's what we're going with. We had three possible CO2 temperature and humidity sensors. We didn't go with the BME688 because it only measures gas. It doesn't measure a specific gas, so there would be no way to tell between CO2 and other gases. We went with the SCD41 because it was cheaper than the SCD30, and it basically did what we wanted to do, so we were okay with this one.
Regulator comparison, we take a look at many of them and we ended up choosing these two that you see on yellow. The reason why we choose it is because the TPS 82130 offer 3 amperes. That is more current than we need, but it's good to have that wide range. And also the accuracy of this chip is 1%. It's very difficult, hard to solder, so we send to the fab house to solder it down. That's why we have a second option, that is the Max 1836. Choosing the microcontroller, we choose one that has the embedded Wi-Fi antenna. This was the most important thing to us since we're gonna do our application over through Wi-Fi. It's gonna be connected to a server. It's gonna be connected to another microcontroller. The ESP32 has the ESP now that we can also use. It needs maximum 250 milliampere if everything is working. It might use up to 350 milliamperes, but we can provide that current with the previous voltage regulator. One of the main reasons we chose it is also implementation. It's really easy since we have a lot of reference everywhere about the ESP32.
The reason why we selected Wi-Fi as a way of communicating it was because we found a better range, a better frequency, data transfer rate, security, and also it supported many devices at the same time. The only drawbacks that we found was that power consumption could be high and also connection complexity could take longer as it requires network setup. We also decided to use Flutter as a way of creating our app because it supports both Android and iOS. Also, the programming language is Dart, which is really similar to Java, and we were used to it. It also has high performance UI and custom animations, which is really important for us when it comes to creating our app. The only drawbacks that we found was that it was the learning curve was really high, and also the app size was also high. For our database, we decided to use MongoDB, and the reason why because it uses a document oriented, which is a JSON-like. It is a non-SQL type. It has many benefits, and some of them were flexible schema and high scalability. We also found some drawbacks, which is limited support for complex transactions, and it is non-relational. We also found out that Heroku was the best way to host our server. It has an easy deployment and it scales automatically. Also, it is really good for web apps, startups, and prototyping. Also, it has a fair pricing since it is only $7 per month. The only drawback that we found was that it has a limited free tier and also cost increases with the more that you use it.
This table compares different types of 3D printing material to determine what material we are going to use for our housing. We mostly looked at heat resistance, UV resistance, and moisture resistance because in a greenhouse there's going to be a lot of humidity and a lot of sun and heat. So we were between PETG and ASA. In the end, we went with ASA because although it has high toxicity while printing, we can print in the TI lab and its UV resistance was higher than that of PETG. One of the optical elements we had decided to use was a diffraction grating. A diffraction grating takes the white light being shown on it and separates it into its components. On the right, you can see a plane reflective grating on the top and a plane transmissive grating on the bottom. They essentially do, as they say, either reflect or transmit that separated light. The reason we went with the plane transmissive grating was because it makes the optical system more compact. And in a straight optical system, you don't need to use mirrors to put the light back on track. Here's a comparison chart of different types of diffraction gratings for purchase. They range all the way from low-quality film diffraction gratings to high-quality float glass diffraction gratings. As you can see, there is no highlighted diffraction grating on there, and we're going to explain that in the next slide. Here is our original optical layout. The part I want to focus on is the part with the diffraction grating on the right side. So as you can see, the light from the sun goes through a filter, which is then sent into our diffraction grating, which would separate that light into those blue and red components, which would then be read by our photodiodes. The reason this is no longer our optical system is because we realized as the sun moves across the greenhouse, the diffraction grating is going to change the position of the red and blue light. So our photodiodes, which are held steady, would no longer be able to read the light.
Our new design is much more compact than our old design. As you see, we have 3 different fisheye lenses. We have our red and blue filters. We still have our 3 sensors, but now we have a new addition of red and blue LEDs, which will change according to a desired ratio within the app and feedback from the light intensity sensors.
Overall Our diagram, I will be focused more on the PCB part that we can see in the left side that we have a power supply that can be a 9-volt battery or a 5-volt USB connector. That power will supply through the USB connector or through the battery. It depends, and if it's through USB, it's gonna go to USB to UART communication chip that going to the ESP32, and the ESP32 will send the signal to our I2C switch. This IC, what it does is split one I2C line into 4 I2C line. Why do we need this? Because we have 4 sensors that they share the same I2C address. Since they share the same I2C address, we need to use different buses of I2C with this IC, and it do a really good job. We already tried it and it's working properly. In the bottom here, we can see that through the USB, of course, we have the ESD protection, the TVS diodes, and the voltage regulator, which provide 3.3 and 1 VA for all the peripheral we're using.
This is a software diagram. A user will have to go to the sign up page to create all their credentials. Once you do it, then the database will create a temporary user, and then it will send an email confirmation to the user. Once you confirm that email, then the database will create a permanent user. Once you have done all of that, then you go to the login page and use all your credentials that you just created and confirm. If the user is valid, meaning that you use the correct username and password, then you will go to the home page. If not, it will be an invalid user and you will have to try again. In the home page, you have two options. The first option is to go to the profile page. In the profile page, we fetch the user data from the database and then we either delete or update your name or username. Once one of those two happen, so the server will either delete or save your data from the database. The other option is to go to the reading pages. We have multiple reading pages where it fetch all the data that is collected from the sensors and it display all of them. And then you also have an option to go from all the pages to either log out or go back to the previous pages.
Here is a quick view to the schematic for the voltage regulator. You can see here that we have three. One of them is do not place. This is just in case the 3v3 fail. So we can provide 3v3 will shut it down a simple voltage regulator. All the footprints here are really big and easy to solder. On the bottom left corner, we can see the USB connector. In the bottom also we can see the TVS diodes. In this page, we can take a look at the microcontroller and the button implementations, a LED that will show us if every power is good in the PCB. It will turn on, and in the bottom left corner we saw the sheet that I was talking about, the IC who has the enter one square line, and it came out with with four square line to communicate with all the sensors who has the same square address. Sensor out interface and the USB to UART schematic. For the PCB stack up, we choose 4 layer, 2 for signal, top and bottom, and ground and power in the middle. In the right side, you can see the power distribution network for this PCB. Here what you seeing is the signal layers, the top on the left, the bottom on the right. As you can see, a lot of components are close to one corner. This is because the sensor needs space on the PCB. All the components are placed on the top layer. So in the bottom layer, we only have connections. Look to the power distribution network where we can see the switch in the top that will communicate to the power in real depending which power are we using. We're using 9 volt or USB. Depending the position of the switch is gonna provide it to the whole PCB the power in.
This is our software design UI. This is how we handle user data. So first, we could go to the login page. As you can see, you have to prompt your username and password. We also have a forget password in case you forget your password. We also have a sign up page. This is our sign up page or register page. So as you can see, we have a full name, email, username, and password requirement in order for you to register a new user. This is our reset password page. So as you can see, it says if you have an account with us, you'll receive an email to change your password. And then this is our profile page. As mentioned before, you will be able to update your name, update your username, or delete your account. First, we have a sidebar menu that's going to help you navigate to all the pages that the app has. Then on the second picture, we could see the home page. In the home page, we have many other pages that are gonna be helpful to read all the measurements collected from the sensors. And the first one, you can see an analyzer of blue to red light, which right now is only reading a lux value from the sensor. Then we have the temperature readings. In the temperature readings, as you can see, we're reading the CO2 level, the temperature, the humidity, everything from a sensor that we have connected to our PCB.
As stated earlier, we had to switch our design because of the movement of the diffraction pattern and the movement of the sun. We had not taken this into account, and what it caused was a large amount of light loss, rapid changes in lux values, and not accurate lux values. And overall, it just wasn't a good design and had a very limited FOV. As shown previously, our new design is much more compact. We're able to get the fisheye lens very close to the sensor, so very little light is lost. And while testing this, it's clear that the light gathering capabilities are much better. There was a lot of calibration that had to be done in changing the integration time and the gain, and even measuring the value that was output by that by another value. And a lot of going both indoors and outdoors to guarantee a matching value with a handheld lux sensor. But within time, we were able to get within 15%, and soon we'll be able to get within 10%.
We also are glad to announce that we already received the PCB and we start testing everything. All the voltage tests good, all the current tests good, powering pass, the LED on we were able to do it with the NCU program, the switch work, the button works. We also test the functionality of the PCB and the power sensor on pass. Communication between sensor is good with the MCU. The Wi-Fi connection is good. It can connect to the website as well. So the PCB is all good. The only little thing that we are spending now is a kiwi connector to connect an extra sensor that we want to use, and that is gonna be soon. But after that, we can say that everything in the main PCB is all done.
We are now going to quickly explain our budgeting and financing for the sake of time. Here is our budget. You see that our total budgeted was around $200 and our total bought so far is around $500. Here is our timeline for Senior Design 1. Here is our timeline for Senior Design 2. As you can see, we have ordered our PCB, started ordering the rest of our materials, and completed our critical design review. Right now, we are doing our application design / coding and building our prototype.
Thank you.